Hello, everybody, and welcome to another edition of Water Talks. We took a little bit of a break there, but you can see hopefully we've got new branding for you, new platform. Thanks for hopefully figuring out Zoom here and being able to join us today. We've got a great presentation going through some advanced water quality analysis, and we've got a special guest, Ben, from Arcadis as well. So a lot to get through today. But again, thanks for being with us here. All right, as for your host today, first, myself, I'll just be kind of doing a little bit here at the beginning. I'm a solutions engineer here at Innovyze, been with Innovyze for almost 6 years doing post and kind of pre-sales support. But again, your main hosts today, presenters, are Ben from Arcadis and Nathan from Innovyze. Nathan, do you want to go ahead and introduce yourself?
Yeah, my name's Nathan. I work in the product management group, working with our developers. I used to be implementing and supporting our software and helping with the sales. And so, yeah, I've been working with the developers, and we just released enabled a new module within MSX that I'm excited to talk through with you guys. But I'll hand it over to Ben to introduce yourself.
Sure. So I'm Ben Chenevey. I'm the distribution system management and planning practice lead at Arcadis. So do a lot of hydraulic models, using them, building them for utilities, but also looking at water quality. That's something that I like to talk about, and I like to look at all those details on the water quality side. So I'm looking forward to sharing some experiences and talking about MSX specifically today.
Yeah, it's awesome to have you back, Ben, by the way. I think the first time you were on Water Talks was back in 2 years ago, like August 2020. You might have been our first kind of guest speaker there. So yeah, great to have you back. I'm happy that I just happened to run across your great kind of AWWA article back in the March issue, I think it was. And yeah, glad you could join us there. Thanks again.
Yeah, absolutely. Me too.
All right, perfect. So a little bit of, again, housekeeping before we get into it. Again, new platform. I'm glad you all could make it on Zoom. That's what we'll be doing from now on instead of GoToWebinar. We're also making another tweak just with the move and acquisition by Arcadis. We're now going to be doing Water Talks every other week. It'll still be Tuesdays, mostly at the same time, but this just gives our marketing group a little more ability to just stay ahead of the different topics and things like that. So there's a list of kind of what we'll be diving into today, very much focused on InfoWater Pro, distribution modeling, water quality analysis, but the next couple sessions will be focused on InfoWorks ICM. After that, we'll be looking at a cloud solution, and then we'll bring another case study to you all. Again, we've been doing these Water Talks for a full 2 years now. We've got a ton of different recordings on other topics. If you do have a topic you're curious about in mind, please do let us know in the Q&A or in the survey at the end. And there's a good chance we've probably already done a Water Talk on that topic and could share it with you. Hopefully y'all can see the Q&A. We will be, reviewing those, trying to get to as many of those as possible. Ben and Nathan do have a lot of great content to get to today, so might not be quite as Q&A focused, but please do put those in there. And yes, this is being recorded right now, and we will distribute the recording. All right. With that, Nathan,
all right,
go ahead and introduce today's topic.
Yeah. So today we're going to be talking about water quality modeling, and especially kind of going into toward the more advanced side. And since we do have a bit of content, we're actually anticipating we might run over an hour this week. So if you've got time and you can stay on till the end and for all the Q&A, great. This is just a quick run through of what we're going to get through. If you can't, you have to drop off, after an hour, no problem. It should still include the full recording. So I'm going to start off just with some really brief updates on our product side, and then I'm going to hand it over to Ben, who's going to give some water quality modeling overview and share some case studies. And Ben just has a wealth of experience with water quality, so great opportunity to get kind of an introduction to water quality modeling if you're new to it, and ask any questions you have, because it's a great opportunity. And then following up with that, we just released a new white paper that I'll share in the help file we have a new MSX model built in as one of the defaults. And so I'm going to explain that model, why it's beneficial, how to get your model up and running and parameterized based on lab data, and then hopefully we'll have some time for a Q&A. So it's going to be a packed session. So I will actually, yeah, to the next slide. One other thing to just get out of the way, in case you missed it, we now have a slightly new look, a light new logoing for InfoWater Pro. This is now a new subscription. So we've significantly simplified in case you haven't seen. So now it's just a one single simple subscription. It's the same price now, InfoWater Pro or InfoWorks WS Pro, and they are now just fully unlimited. So unlimited size, unlimited modules. So all of the modules that we used to sell, add-on fees, and we tried to customize all these solutions. We just, you could just have it all. And so importantly for this talk is now MSX is going to be bundled into all new subscriptions. And so before, some of what we're going to talk about used to be exclusive to modelers that were really serious about water quality modeling. Now, I mean, of course, you don't just casually get into water quality modeling. You do it for a reason, and it requires a bit of data. But now anyone that wants to can start to explore MSX modeling and so on. So that's a little bit of the timeliness of this webinar. I should mention currently the Surge engine is not included. That's a separate conversation for you with your sales representative if you're interested in that. And also just mentioning that we now have the new Autodesk licensing. So there's many benefits of us now being part of the Autodesk ecosystem. The licensing is in particular much more streamlined, easy, simple. You can just take your user login with you wherever, and the installers and things like that. There's a lot of benefits. I'll show one other thing once I'm in the software, showing it later. But that's just a quick update, is that now everything's included. So I'll hand it over to Ben to kick off with some water quality modeling. And you can
Excellent.
take the screen sharing.
Looks like, there we go. Share my screen real quick. Okay. So yeah, we wanted to talk about water quality modeling today. So two key things that I wanted to go through was providing an overview of water quality modeling, kind of what it is. We're going to talk about multi-species modeling and MSX, so what that is and how it relates to other types of water quality modeling, as well as provide an example, kind of a case study with the city of Canton, how MSX was used for that system, what we looked at, and then just some of the results and recommendations that came out of that study, just to get us kind of thinking about water quality before then hand it back to Nathan to talk more specifics about InfoWater MSX. So first up, distribution system water quality modeling is always built on top of hydraulic modeling. So before we can get to water quality, we have to have a hydraulic model of the distribution system. And that has to be accurate. You get reliable hydraulic results before you do the water quality portion, because we're building on top of that hydraulics to look at water quality. It does also have to be an extended period simulation, so we can't do a steady state simulation. But once we get to actual water quality modeling, there's actually different types of water quality modeling. First, we start with hydraulics-based water quality on the bottom left there. And that's really water agent source traces. So typically high-level indicators of conditions in the system. That's different from the two boxes on the right, which are more constituents, where we're looking at actual concentrations out in the system. So that might be looking at free chlorine concentrations, THMs, or other disinfection byproducts. And we have two different categories there. There's the constituents that are built in, which those are both built into InfoWater and then the EPANet algorithm. So kind of simplified methods of looking at things like free chlorine and THM. versus advanced water quality modeling, which I usually separate. Like Nathan was saying, it's a little bit more built in now with InfoWater than it has been in the past, but it is a separate module. And it's more complex. And that's one of the things that we want to talk about today of what that actually entails. But with that MSX module, you can start to look at more complex reaction and more advanced capabilities of water quality. And just wanted to provide a little bit more detail of both of these. So on the hydraulic side, these are, like I said, water age and source trace are the two main hydraulic water quality simulation options. Water age is really common for looking at high-level indication of what water quality is, identifying where dead ends are in the system or where areas in the system aren't circulating as well, or maybe just kind of stagnant water issues. It is pretty high level in that it can vary pretty significantly what actually constitutes a water quality issue. Does 5 days in one system might be totally fine, but in another system it actually might mean some major issues are occurring. So it gives you an indication, but not the full picture necessarily, but still very easy to simulate in the model. Hydraulic traces are somewhat similar in that they're an indicator of what conditions you're actually seeing in the system. So we can look at traces of, say, the treatment plants. If there's multiple treatment plants, identify what the service areas are, what the mixing boundary might be. We can also trace other components like pump stations or even tanks to look at influence areas around a storage tank. So kind of understanding the system, looking at the hydraulics and where the water is moving. So next is constituent modeling. So that's where we're actually looking at concentrations. Here, since we're looking at concentrations, we do need to provide more information on the modeling side, usually through calibration of different parameters based on sampling data. So on the free chlorine side, the first order reaction is built into the system. So that's the default method that's included in just normal InfoWater or EPANet. And usually you have to specify for example, bulk decay rate or a wall decay rate. You have to calibrate those values to the specific system and to the specific water quality conditions. Similarly, you could do THM, but it is limited to a formation potential method. So looking at bulk saturation growth, for example. Usually when we're looking at constituents, we do have to start looking at sampling data out in the distribution system as well as at the plant. And how we actually come up with those values, those KB and KW values, for example, depends on what data we have and how much data we have. So the next step after having a built-in constituent model is looking at MSX, and that's the advanced water quality modeling that we're kind of focused in on today. MSX does multi-species modeling. It was originally released in the early 2010s by EPA, kind of as an add-on to EPA Net, but it's also been incorporated into the commercial products and InfoWater Pro. And really how it's doing that advanced water quality modeling portion is being able to define and support species, like whatever species you want to look at, and then their individual reaction rates and interactions with each other. So instead of just looking at a disinfectant residual, so free chlorine just by itself, simple representation, we
Uh-oh. Did we lose Ben?
Yeah, we may have lost Ben.
Shoot. I blame the new platform.
Yeah.
Do we want to
Let's see. We could do maybe a quick poll question because we still have the rest of the audience, and I hear you. You hear me? Oh, Ben, you there?
my back?
Yes, you're back.
Okay. Just got an internet unstable. It's all the snow outside.
Oh, gotcha. Hanging on.
Okay. So okay. I'll keep going. Hopefully I didn't cut out for too long.
No, yeah, yeah, just a minute or so.
Okay. Okay. Cool. So we have all these different components that can be simulated in MSX. So not only disinfectant residual, but the total organic carbon, the water temperature, disinfection byproducts, we can link into that disinfectant residual component and get a more complex interaction of all these different species with each other. So some more details about multi-species modeling with MSX. It has different components. Like I said, we can define whatever species that we want to actually simulate, and we can define what their reactions and their equations and interactions with each other. We can also include different parameters that help us define those interactions, as well as what the boundary conditions are, what's actually going into the system. Typically, these models don't include what's actually occurring at the distribution or at the plant. These are usually starting at, say, a clear well, but we have to define what's actually going into the distribution system. We also have a number of different use cases. We can combine separate scenarios into one, even if those species don't interact with each other. We can actually include them in all one simulation. For example, looking at water age and multiple source traces all at once. They don't influence each other, but we can simulate it together. We can look at higher order reaction rates, which I'll get into in a couple slides, just more advanced analysis of chlorine decay rates. And then also just adding additional reactive species as part of modeling those, for example, free chlorine. And we can look at planning level water quality analysis, but also start to get into the predictive water quality modeling, looking at more details and more understanding of what's actually going on in the system. There's also a number of challenges associated with MSX. First and foremost is really the complexity. So you have to define all of these interactions. You have to understand some of those water quality terms that kind of go into that MSX model. Once you develop one of these MSX models, you can reuse it, and it becomes a little bit easier to actually change and tweak things going forward, but you do still have to have some understanding there of water quality. Simulation time is also higher than normal InfoWater simulations. MSX could run, and that depends on the size of the system, but the complexity of the model. But it could be, half an hour. It could be multiple hours simulation time. That also depends on the integration method. So there's different integration methods that influence simulation time and accuracy. And that also influences what tank mixing models are supported. So not every mixing model for tanks is supported depending on which integration method you choose. Looking at how MSX ties into a model. So you can think of an MSX model as an additional data set. In InfoWater, we have different scenarios that have maybe different simulation settings and different data sets like demand sets and pipe sets, facility sets, which might have different physical characteristics or physical pipe sets, active or not active. And an MSX model kind of fits in with that. So you can develop an MSX model and then use it for multiple scenarios as kind of a building block. Each MSX model includes a number of different components, but the key ones there are the species. For example, the water age or free chlorine, that's what we're actually trying to simulate and get results for. And then the terms field is where we're defining the rate expressions, the formulas, the interactions between different species. So that's where it gets the most complicated. We also have the capabilities for constants and parameters that we can use. For example, the bulk chlorine rates. We can input that and have that as a constant from a certain treatment plant. We can also have parameters that influence individual elements. For example, an THM aeration we can model, and that specific tank or specific tanks in the system might have a aeration removal rate parameter that we could tie to it. And then multi-species node quality, basically the initial conditions. That might be the initial conditions throughout the system that the simulation starts at, but it also includes what the treatment plant is providing to the system. So that provides a quick overview of MSX and water quality, and we're going to dive into looking at a case study of how the city of Canton used water quality modeling. So the city of Canton is in Northeast Ohio. It provides water to about 100,000 customers. They do have 3 individual treatment plants, all groundwater, and then their average production is around 20 million gallons per day. So as part of a larger project, we did develop an InfoWater Pro model for them, representing their entire distribution system, 2-inch and larger, about 670 miles worth of pipes. We do have future system scenarios as well as existing system scenarios in that model as part of the kind of full master planning effort that we did for them. But it is also able to simulate hydraulics. And we did calibrate those conditions, those hydraulic conditions, but we also looked at water quality. So within this water quality model and this MSX model specifically, it can simulate free chlorine concentrations, total THMs, and then source traces and water ages all at once. So I didn't do too many equations, at least in this presentation, kept it minimal, because sometimes when we look at equations, there can be a lot of different numbers in there. But just as an example of what we did with the city of Canton, we ended up selecting a specific representation of free chlorine. So there's multiple ways to simulate free chlorine decay in the system. Like I mentioned at the beginning, the first order decay is what's built in with EPANet and InfoWater. It's kind of the standard approach, but it doesn't necessarily represent actually what we see in a distribution system. You can kind of see that on the right there with the green model there. There's the first order model where it starts out at a high chlorine concentration and decays, but it actually keeps decaying. What we usually see in the system is that it sometimes flattens out a little bit more than what a first order decay can actually simulate. And that's why second order models are typically a little bit more accurate. Now, when we get into second order bulk decay rates, there's different ways and different methods that you can actually do second order. A lot of the time, my go-to method is a 1R or 1 reactant method, where we're actually not only simulating chlorine decay, but actually in MSX, we're simulating what it's reacting against. So the kind of the organic content that it's reacting against, and that is contributing to the decay rate. There's also, in addition to 1R and single reactant, there's 2 reactant models where it gets more detailed, more parameters, but even fine tuning what that representation looks like. For Canton, we actually went with a parameterized approach. So that was developed and kind of published by Clark back in 1998. So it's been around for quite a while, where we're not explicitly simulating that reactant, what chlorine is reacting against. We're instead converting that to these R and U parameters. The reason why we ended up using that was because the city has a lot of routine samples out in the distribution system, but they don't have a lot of, for example, chlorine jar tests from the plants, where we're like a lot of detailed lab information. And Nathan's going to talk a little bit about that later too, but they didn't have a lot of that. We did do a little bit of sampling just to make sure, see how the plants reacted and how similar they were from each other in terms of chlorine decay and THM formation. But all 3 of them are groundwater, so they behaved pretty similarly. So that's kind of why we went with that approach, just the amount of data and what we were seeing out in the system, just a simplified approach. But like I said, we could do all 3 of these and even beyond and more complex representations as well in MSX. So we use that routine water quality sampling data and regulatory data out in the distribution system to develop decay curves and specifically those parameters. Looking at the data, we saw for the most part, their system actually stayed pretty similarly throughout the the year in terms of free chlorine residuals, except for some periods during summer conditions. We're looking at that, and we're looking at what those locations were. It was probably influenced based on some nearby storage tanks that had some pretty high turnover rates, so they could be actually getting higher temperature and causing that decay to drop further than other time periods. But what we ended up doing was looking at a typical condition and then a worst case condition that occurred in those summer months, and then developing those specific parameters for the different plants and different conditions with those R, U, and KW. The wall decay component we looked at out in the system, just kind of tweaking those numbers based on what we were seeing in the system. We also simulated THM. So again, looking at regulatory data for THM samples out in the distribution system. The city thankfully doesn't have a significant THM formation issue. They're primarily groundwater, so they're relatively low water THM formation. But they still wanted to look at it and see if that changed in the future. What conditions might be producing some of the slightly higher values they were seeing in summer months. And that was parallel to what we were seeing with the free chlorine drops. So in the model, that THM formation is simulated with a yield factor. So as chlorine decays, there's a yield factor that actually calculates and contributes to the THM formation. So we calibrated that THM yield specifically to the system, and then we're able to simulate that formation, kind of similar to what you see in that graph. As chlorine decays in blue, THM forms on the red. So getting into some of the results, this is an example of just parallel simulations that took place. This is looking at water age, water quality variability, and then the mixing areas, so the source traces, and just simulating all of those together within MSX. So we could identify where the issues are with higher water age, kind of on the fringes of the system, variability, both in terms of water age and chlorine, especially surrounding their storage tanks, and then the mixing areas between the different plants, because they've had historic challenges with some of those mixing areas. We also combined all three of those results with things like the chlorine simulation results from MSX. So we were able to look at average conditions, summer conditions, understand what the differences are between those two conditions, what the actual chlorine concentration was the model was predicting. Having that chlorine component just made it a little bit more actionable when we were starting to look at improvements and evaluations of the system. Does that water age get impacted, but by a couple hours, what does that actually mean? Maybe we could look at the chlorine residual and see, is that actually going to make an impact on the chlorine residual? Is it a relatively minor impact? And we looked at a lot of different things for the city of Canton once we had this model. So we were doing a full master plan project. We looked at issues in the system that the city had identified or that the model had identified, and how to look at solving those or improving the system. One of the key aspects was eliminating things like dead ends or areas where historic customer complaints had occurred. They also had an area where they were using quite a lot of water for flushing the system, just because of those historic complaints in the system. So we were able to look at this area and figure out what the model was predicting, but also identify some improvements to the system. This particular area that I was showing on the right is actually a boundary between the high and low pressure zones, which made it a little bit challenging to just connect some pipes together. So we actually did a combination of, or proposed a combination of converting some pressure zones from high service to low service to help circulate some areas and eliminate some dead ends, as well as providing a connection from the high pressure zone to the low pressure zone and reverse the flow through a small dead end area instead of using flushers and just flushing it through the system. So they're not only able to flush that water, but to remove that non-revenue water component. With the MSX and water quality model, we were able to simulate that and understand what is the impact to water age, what is the impact to free chlorine residual, and these other components that we're simulating, as well as understand exactly on the non-revenue water side, how much water are we actually saving with this approach. Another example of something that we looked at was looking at reducing some of their storage in their system. They had a particular reservoir that they were looking at rehabbing anyway. And so we investigated, can we reduce that storage size and what kind of water quality impacts does that have? We saw a pretty large influence area from one of the storage tanks. As you can see on the right, these red and blue colors are where the water in the tank could influence those areas. And actually that's some of the areas correlated really strongly with those areas that we were seeing those low pressure or low chlorine residual results sometimes in the systems. So it was obviously having some turnover issues and oversize. So we looked at reducing that storage volume and again, understanding what the water age impact was, but also the chlorine residual impact, where they would be able to actually see that out in the system with their chlorine residuals. I think some of the sites saw an improvement of around 0.2 milligrams per liter. So we're maybe at 0.4 milligrams per liter on the low end, maybe it would be a 0.6. So a decent bump in chlorine residual. On average conditions, they might not see as much of an impact, but obviously that variability and how it changes actually throughout the day, we looked at in the model. For the city of Canton, they don't have a THM issue or challenge out in the system. So we didn't look at things like THM aeration, but that's something that we've looked at for other systems is looking at storage size, looking at operation, but also things like technology improvements. So putting a THM air stripping out in the storage tank, what does that actually change in the system? Can we get a certain percentage removal rate? And can we actually positively impact the THM out in the distribution system? So we didn't look at that with Canton, but that's a common use case for for MSX. Another one is also looking at operations. So again, with City of Canton, they only have groundwater. But if you have both groundwater and surface water, you can actually look at operational changes. And the MSX model represents all of those different, decay rates for groundwater versus a decay rate for surface water. And they might be different. And the THM formation might be different. And the mixing out in the system is modeled. So we can actually look at operational changes to see what we can influence and how we can influence it. So just as a summary, water quality modeling is obviously a critical component of managing the system between regulatory requirements, minimizing customer complaints, improving the system. And water quality is complex. So with an MSX model, you can obviously get a different representation. It's not going to be exactly the water quality conditions out in the system, but it's a better representation than some of those built-in methods. And once we have that representation, it can be a critical component of predicting what's going to happen out in the system and mitigating some of those poor water quality issues or improving on those water quality issues. And then I think in general, MSX is a really powerful tool. Like I said, it's a little bit more complex, but it's a really powerful tool to have in your toolbox and combine with things like water age and source traces and getting the full representation or a better representation of chlorine decay and DBP formation out in the system. So that's all I had. I think we're going to switch back to Nathan to talk more.
Yeah. Yeah, Ben, before you drop your screen share, there were a couple
Yeah.
questions related
Yeah,
to those
yeah.
projects. Yeah, so the first one, I'm not used to to Zoom webinars. I'm going to click answer live. So curious if Canton determined the THM yield rate via bottle testing or another method. Did you do that with their data?
Yeah, we did do one set. They don't typically do that since they don't have high THM out in the system. So we did have them do some jar tests at each of their plants just to see, at least in that time period. I think it was like maybe in the spring time period. So not in their worst case conditions, but to see how much formation and yield actually was occurring at the plants. So we did have a set of data. And then we also looked at that and compared against what was happening out in the system to see if that might change under different conditions.
Okay, thanks. And then one other question. Were the modeled chlorine levels for summer conditions and then confirmed through sampling in the system?
Right. The summer conditions were confirmed with some distribution system sampling data. We looked at multiple years and saw a pretty consistent trend of those lower chlorine values in a couple of the hottest months.
Okay. Great. Okay. Well, I'll take the screen share. Let me.
Yeah.
Yeah. I guess you can. Once you stop sharing, yeah. Now I can share mine. All right. Can you see my PowerPoint?
Yes.
All right. Great. Just wanted a quick confirmation. All right. So I'm going to be talking.
Did you want to do those couple of poll questions, Nathan? Or?
Oh yeah. Thanks for the reminder. You want to kick those off, Tim?
Yeah, a couple poll questions here. Let's see how this works.
All right, yeah, I'll read this off. So yeah, after kind of going through that introduction, we're just really kind of curious as we're exploring development roadmaps and so on. Always just looking to keep a pulse on the industry. I know there's a number of experienced water qualities I'm noticing in the participants list. But yeah, this question is, how do you expect your organization will leverage water quality simulations in the next 3 years? And this is, a multiple choice, so check any that apply. So I'll let you just kind of pick through things. Anything that stands out to you, even if it's you think the organization would like to, and also if you're a consultant, maybe you can speak to, what some of your major projects would be dealing with for municipalities. So we'll just take maybe a few more seconds on that one.
I think that's pretty good. We got up to 70% participation there. So thanks, everybody.
Great.
Let's see if I can share these results. Yeah, let's take a look.
Awesome, great. Yeah. So water age is usually what we see as kind of the dominant age, just because it's such a useful tool, and so long as you've done the hydraulics, it's pretty easy to run, and there's a lot of benefits that you get out of it. So great to see that one strong. Water source tracing next. I'm pleasantly surprised to see 47% interest in MSX. I guess we probably do have a little bit of a biased sample of the modeling industry on this call, but that's good. And 23% for kind of looking at more operational support for real-time events. So that's exciting. Okay, and then I think we have one more question. Yep. Yeah. So this question. So you may know MSX runs can take a bit longer, and usually with water quality simulations, you may need to be running much longer times, like multiple weeks at a time. So this is just a question on cloud computing. If you had access to cloud computing for water quality simulations, would that be useful? So yes, my simulations usually take a bit of time. I would definitely be interested, or maybe probably not. Desktop computing is sufficient. or probably not because it would be difficult to get the IT approval to run a model in our cloud environment, or they would not be useful to us at all, either on desktop or in the cloud. So your answers here will be helpful. And just kind of curious about the state of the industry. I know that many simulation-based industries are heading more towards a cloud-based approach. All right, Tim, we could probably wrap that one up. Okay, yeah. So a fair share, like a quarter, interested, and a good number. Still, it's difficult getting IT approval. Okay, not too far off from what I would have expected. So thanks all. And I believe I'm still sharing my screen. So next, I'm going to transition into this new built-in chlorine decay model that is included in one of the defaults within MSX. So I'll get started. So before I move forward, this is something that we did not initiate and do on our own. We've actually been talking with some researchers in Western Sydney University, namely some of the people in this paper. And I'll just highlight one thing out of this paper is that these guys have been in this field for a number of years. They have a number of publications, and this was an important paper back around 10 years ago, where they evaluated a number of different water chlorine models within municipal distribution systems, and they kind of evaluated different models out there looking for essential features around things that are accurate and simple and computationally as efficient as possible, while still being able to describe varying initial chlorine dose, variations in temperature, and successive rechlorinations. So they've been in the space publishing papers for a while, and we worked with them. They did a bulk of the work. These two authors helped us with a white paper that's now freely available in our help file. I'll share the link just now. If I get back to my chat panel, I'm going to click send on this. Actually, I don't see the send icon. There it goes. All right, so that should be now in the chat. So this is a free paper that will summarize this model that I'm about to talk about. It'll teach you about it, why it's beneficial, and more importantly, how to get up and running with it successfully. So going from the lab data to parameterizing your model, and being successful with it. So that in a nutshell is what I'm going to give a quick overview for those that don't have the patience to read a research paper. They did take it a little bit, it's not quite as academic as a typical research paper. It's brought down a little bit more to a little bit more practical level, but happy to have worked with them. And also we have their contact information, and they have worked with a number of municipalities. So if you have questions on water quality or you're interested in some of their services, they go above and beyond some of the things that are in the paper. So yeah, if you're interested, by all means, you can reach out to them. All right, so moving forward, so just brief overview, just showing a few equations on some of the different methods to model chlorine. So there's first order chlorine decay, and this is what is kind of in nearly all off the shelf water quality modeling tools like EPANet. The change in chlorine is equal to negative, so it's decay, and then you have a decay coefficient times the chlorine concentration, and you can add an exponent if you want. And so this is going to give just that kind of exponential decay that you would expect. I'll talk about some of the limitations. So second order decay typically is everything is the same, but we add on this other reactant. So this is R. And so what this is we assume the concentration of reactants varies over time and space, and it plays an important role. So in first order decay, it's like we're assuming that chlorine is reacting with things, but those reactants are limitless, infinite, and they're always present, and so it will always keep decaying. And that's one of the problems with this model, is that, Ben mentioned these usually kind of flatline eventually, and they kind of stop decaying. Whereas first order decay, it will just keep decaying no matter what. So reactants, in reality, what we see is that these also start to decay, and so the rate actually will decay, or will slow down over time. And the next kind of step beyond that is parallel second order chlorine decay. And so what we're doing is the same principle, but now we're considering that there are multiple reactants. Here's kind of the summary text. Here we assume there are multiple reactants with different reaction rates that vary over time and space. And so now the decay rate of chlorine is the sum of these different decay reaction equations. So from that paper that I highlighted earlier, they did a study. This was in Australia. They had some chlorine data from 3 different locations with 3 different starting initial chlorine doses, and they did this samples up to 70 hours. And in these conditions, you really start to see where first order decay really breaks down. So for starters, I mean, obviously at the end, this one is, initially it's under predicting the decay, and then it's way over predicting the decay. But also, if you have the initial concentration, this line is always kind of proportional to that line. You only have one coefficient to calibrate for everything in the system. And so while the first one by the end is way over predicting the chlorine decay, this lower one is way under predicting the decay. And so you don't have that resolution capability. Also, what we see in a lot of waters is that there's typically a fast initial decay rate followed by a slow residual decay rate. And so that was kind of one of the things that they saw as a characteristic in the water. And that is kind of what led them to focus on this 2 parallel reactant chlorine decay. And so here they were able to take this set of data and come up with a single set of parameters that was able to fit in all these different cases. And so they, and from their focus and their explanation, they're focusing on what is the most simple and efficient approach, what can predict chlorine decay for many hours. So, you can actually fit first order decay, within 8 hours, usually pretty well. But once you start to go beyond that is where it usually starts to break down. And they're also looking for something that can handle varying initial concentrations and temperatures. So they recommend this 2 parallel reactant model. And so that's what I'll be talking about. I will also kind of just give a preface that this was one study, what they found to be for this water. If you have had consultants, do a study for your system and they used a different model, that could very well be the right model for your data. So I don't want to throw every other model under the bus. It's always a decision of what data you have. Also, any given source water is going to behave differently. So take this all with a grain of salt. But this is, I would say a good tool to have in your belt to consider. So all right, let's get into the model. So to do this model, we have 4 species, and these are the acronyms that we use within the MSX built-in default. So FCl is free chlorine. Then we have a reactant of fast reactants. We also have a species of S for slow reactants. And optionally, you can include the THMs, or you could remove that, or you could, not use them if you want. And then the equations for the bulk decay is pretty standard. So F decays proportional to the product of the chlorine and F times your coefficient. Same with S. And then the decay of chlorine is the sum of those 2 decay rates. and then your THM is that same actual rate. Whoops, I forgot some parentheses. This sum should be in parentheses. Sorry, I'm just noticing that now. And then we multiply it by a yield rate. And so this number is usually somewhere around like 0.045. So that means for every milligram of chlorine that you lose, you gain 0.05 milligrams of trihalomethanes. So that's just kind of a simple yield rate. There's a proportional production of THM for every gram of chlorine that you lose. So those are the equations. It's already kind of built into MSX. And then before I jump into the software, how do we handle temperature? So the problem that we see is that temperature changes can dramatically affect the decay of your chlorine. Some studies have shown that even just 6 degrees Celsius can double the decay rate. And this is a big problem with, some models, if you spend all this effort to calibrate a log, or a, first order decay model, it's not really going to be relevant to any other event, on any other given day. So if we can include temperature into the model, then you can come up with one set of calibration that can, simulate multiple different events. So you could even then look at optimizing your treatment dosing for different seasons. And I've seen that in different studies. So the solution is we measure lab samples from varying temperatures and initial concentrations, and then we fit the temperature impact using an EOR coefficient. So I'll show that process. We also have to make an assumption that the water temperature within your system is relatively consistent for a given analysis event. So that's an important assumption to make. But so we can define a coefficient. EOR is kind of the activation energy divided by your gas constant, and we can come up with a T coefficient, a temperature coefficient. This is an equation. This is all explained in the paper, so I'm going to try to not get stuck on this. But we come up with a reaction coefficient for your fast and slow reactants that basically just varies by temperature. So based on any temperature, TC, you can then just come up with what your updated reaction rates are based on that temperature. So once you find KF20 and KS20 through the calibration process I'll show, then any temperature, you just plug it into this equation and you've got reaction rates that are going to work for your system for that temperature. So these numbers highlighted in yellow are what you are kind of parameterizing from your lab studies, from your bulk decay studies. And then green is something you plug in for any given event to get KF and KS, which is what you plug into the actual model. All right, so I'm going to jump into InfoWater Pro now to just show a quick sample model. Let me just check how we're doing on time. Kind of not too good. So I'm gonna move quickly. Let's see. One thing I do want to point out, if you do install the latest version of InfoWater Pro, you may get a pop-up box that looks like this. You can find it within the command center. This is just one of the features we're gaining from being now within the Autodesk system. They have capabilities just to be able to track how users are using the software, and this helps us to make better decisions about where we are investing in improving and advancing the software. This is optional, so fully optional. If you want to participate, it's just a checkbox. And if you say, I want to participate, we don't store or track any personally identifiable information. We just track, how often you open the software, what kind of runs you do you use MSX and things like that. And we just track some of that water usage software usage information, just like almost every other software in this 21st century. So if you're not comfortable with that, you just uncheck that box, and we don't track anything at all. So just wanted to mention that and explain it before you see it. And if you're curious, you can go to the privacy statement and learn more. So if you want to get into MSX modeling, within InfoWater Pro, what I do is I have a scenario for my MSX model. You may need to look at your time setting to perhaps extend out the duration. Here I have a 14-day simulation. You want to use a smaller quality step and make sure that your hydraulic time step is not too much larger than your quality step, keeping those somewhat in sync. And then for your simulation options, what you do is you go to quality, and in order to access MSX, you choose this advanced option. And so if you are not on our subscription yet and you don't have MSX as a module, this will be grayed out. But once you have a license that has access to it, it's optional. And so, normally you might see none, or this is what kind of standard water quality looks like. And so when you choose advanced, you can choose one of the built-in models, and you can start to customize it. So this is the model. And what I've actually done is I've actually cloned it, because the parameters can change based on temperature. So what I would recommend is when you get the model, create a clone of it, and then you can include in your description what is the temperature that you're running that simulation on, and then use that temperature to update your constants. So I'll just skim through this real quick. So these are my species that I showed earlier. Chlorine, the two different reactants. Really, we're just using a single bulk rate equations for the pipes and the tank terms. These are the terms. These are those equations that I showed. And we have some kind of simple description. We're not using any parameters, and then we are using constants. So constants are just those two different decay rates and the THM yield rate, if you want. These could be parameters. So the difference between parameters and constants is that parameters can be varied at each individual pipe and tank, whereas a constant is just simply constant. So that's just a quick walkthrough. So what you could do is you can take it, you click Save As if you want to create a copy, or you can just try this out of the box one. This one is using parameters that were used within a study in Australia. So it should be reasonably ballpark, but it's not going to fit your model. So it will help you get an idea of what the numbers may look like, but it's not the right numbers for you typically. So just a note on that. And the other thing to do before you run the model is to define your initial concentration. So in this simple model, we have a reservoir here representing my treatment plant. And to set up the concentrations for water quality is you click this little water quality sample beaker, maybe. This is your standard water quality that you may have used before, where you just get initial water quality. But with MSX, we kind of expand that. So if you click this, for a given node, you can input multiple rows. So I could, copy and paste that ID. So you just add the ID of your node, and this one doesn't have an initial THM. Usually THMs coming out of the plant are 0, so that's why I left it out. But if I wanted, I can include that. I'm going to just close that. And you can do that for your reservoirs. If you want to do that for tanks, you can do that for tanks as well. So what you would do typically is you'd maybe run the model for a while once you have it calibrated, and then input the initial, the final results, make those your initial conditions on your tanks and so on to kind of hot start your simulations. You can actually do that also on any junction. And so if I just show this drop down, you can open that table for the current selection as the default, or you can open it for a domain, or you can open up the whole table. So this is something that you can add values for every single node, for every constituent, and you can actually just copy and paste in from Excel. So that's how I did that. And there's one of these tables per MSX model. So if you do a new clone of it, this will be a set of initial conditions specific to that event that you're modeling. All right, and then you just run. I'm not going to run live for you since I'm running out of time, but here's just a quick look at some results. So then you'll see your chlorine concentrations, your fast-slow reactants. So this is a tank where you can see chlorine decays. As it decays, the THMs rise up and start to plateau off. We can take a look at really any junction, take a look at its results. This is a 2-week simulation. So the chlorine is starting to kind of drop down. Let's take a look at just how those fast and slow reactants behave. Generally, the F will decay pretty quickly. This one is actually sustaining a concentration. Kind of depends on where you are in the model. Whereas your S decays much slowly, so this may build up or reach a plateau later on in your system. And then your THMs is what you might want to create maps for. So within that, you could store some custom map displays. Here I have like a junction THM. Let me just, actually I meant to right click and just apply map display. Whoops, I was on the initial time steps. That's not going to be very interesting. It should be just 0 across the board. And it's reading from my result file that has 2 weeks worth of data. So now we're going to jump up to the 280th hour. Might get some actual junction information. There we go. So now we have some higher THMs at different points in the system. Of course, you could also create contour maps as we usually do, or as you do with other things. So here's some contours of your chlorine concentration, and so on. So that's just a quick look at the MSX model. And I'm going to jump back to PowerPoint, and I apologize for those that needed to drop off at the end of the hour. I am just going to show some things real quickly on model parameterization and fitting the model data with Excel, and then we'll jump to a Q&A. So sorry for those that need to drop off at the end of the hour. I see there's not too many additional questions that aren't answered yet, so I'll plunge forward to wrap up. So to get this up and running, you'll obviously need to start with getting some sampling data. So in that paper, they recommend actually to get, if you have varying sources like a surface water treatment plant, as well as different groundwater well boosters, you would need to get sample data for each of those, because those can have different water quality parameters, different initial concentrations on those fast and slow reactants, and so on. If you want to account for varying temperatures and have that dynamic flexibility down the road, get samples at varying temperatures, and then you can calibrate that EOR coefficient. Also, if you can, get varying initial conditions on the chlorine concentration. And also, so these ones will be your lab bulk samples to get the bulk decay, but also, of course, get some downstream concentrations to validate your model and do the pipe wall reaction coefficients. And then once you have all the sample data, I'll show in Excel how you can model the bulk decay using Excel, or Aquasim is actually what the authors use. That is kind of an executable that you can download, and it has built-in tools to help you simulate and optimize your coefficients to fit a water quality model. So that's what they use, they recommend. I went ahead and just did it in Excel, so I'll show that process. And then you're actually fitting your lab bulk decay for 5 different coefficients in parallel. So it's a little bit more tricky than simple first order decay, but I'll show that process in just a minute. And then you simulate. So you add these coefficients into your model, parameterize the model with your initial conditions, and then you simulate, check against your downstream conditions, tweak wall reaction coefficients as needed to achieve a good fit in the model. And then you can do your different studies, look at different dosing strategies, and so on. So now I'm going to switch over to Excel and just play around with some numbers to give you a feel for this model. So this is a model where I have, these are my 5 coefficients that I would need to calibrate. And then I have 4 different events. So here I have events with varying temperature and also a varying initial chlorine concentration. And so each of these events, in this case, I actually, so I just put in my observed data at different times. And then this is my simulated model data. So you're kind of just curve fitting. And then I'm also calculating the root mean squared error for each of those events, coming up with an average one. So once you have this, if you want, you can manually play with it. So here I already have a good numbers, but let's just play around with if we raise the KF 20. So if I go with like 0.2, things are going to decay faster. So if I go to like 1, things are going to cut off down, really steep right at the beginning. If I make this 0, you're only now using the slow decay. Let's go to like a 0.2. And you could, so let's say I overestimate on that one. Let's raise this one up a little bit. So now we're going to add some decay. Actually, let's lower this one a little bit more. We can just kind of play with some things. So as you lower this one, it's going to start to flatline more at the end. And you can also play with the initial concentration. So like I could make this one a 6 and this one a 1. And so on. So you can manually play with it to get a feel for things. Also, if I change the EOR, this will affect how temperature plays a role. So if I make this 90,000, I meant to do 9,000. There we go. So you can play with this, but how do you actually optimize it? I should also mention, just real quick, let me unhide. I'm actually simulating each of the different constituents with a 15-minute period. Pretty simple, just like an explicit model quality or water quality approach where just like in the models, the free chlorine is equal to the previous one minus the reaction rate. So it's pretty simple to set these up. So you simulate it out for each of those, and then I'm just doing a VLOOKUP on my simplified comparison. So let me just hide those again. So what you do is once you have measured data, you have dynamic models for each of these different events, is there's a free plugin to Excel called Solver. So this is Solver, and you can set an objective. So I'm pointing the objective at my root mean squared error cell, and I want to minimize it. So that's the cell, I minimize it. And then I say by changing variable cells. So now I'm just pointing at all these green cells. So now it's going to vary the numbers in these green cells to try to minimize this cell. So somewhat straightforward. Solver, I think it's just something you can actually Google it. It's something you may need to enable going into the Excel options. If you want, you can add some different constraints. So I could say, make it so this EOR does not go above, I did 90,000 and that didn't work. So don't try 90,000. Maybe let's try like don't go above 13,000. And so that's pretty easy. I'm just going to click OK, cancel. So now I have that. So currently I just set them all to be at least above 0. So that's pretty simple. And then you click solve. And I did it last night. It actually gave me a little bit different answers than the original numbers. But what it did was it can make some of these numbers compete with each other. So what ended up happening when I ran it last night is this decay rate went down, but then the initial concentration went up. So I could have just set some different limits. I can run that maybe during the Q&A if people are interested. But you just click solve and it will show. Here's a proposed set of numbers. Do you want to keep it? Do you want to use it or not? And so on. So that's Solver for anyone that is interested in playing around with that. But these were my numbers that I had before. And that, I think, is all I had for the model fit. The actual THMs, as was mentioned, you can just grab water quality samples out of your treatment plant, and then you take measurements of your chlorine over time, as well as the THMs, and then you just fit a single yield rate. As one decays, the other one gets produced, And so you can come up with a fit. That's mentioned in the paper, as well as also some comments on the bulk decay, or the wall reaction coefficients, and some interesting new models that the researchers have been dabbling in. So that's something interesting you can follow up with them on, or read into their papers on that if you're interested. But that is all yeah, so that's the main presentation. Let's take a look at the Q&A. I'll just bring up my model in case there are questions to jump to. So I guess, Tim, first off, any questions you think might be priority to jump on?
I think main thing for folks out there, especially those that might have jumped off, is what have we and can we make available to folks after this who might not have caught this last bit and want to re-look at some of these things, right? So we're definitely going to make the recording available. Nathan's posted that help file site that includes really the paper where a lot of the study was done. There's a question in there. Can you share that spreadsheet? That looks pretty sweet, Nathan.
Okay.
And then
yeah, sure.
I think we'll definitely be able to share some of the slides from the Innovise Autodesk side. Ben, is that okay if we, not to put you on the spot, but we'll circle up and see what we can share and what we can't. But I think just for folks on here that are loving what's being shown and would like to look at it later, I guess we will be making as much as we can available to folks after this. Beyond that, I think there's kind of one key question, and then we can wrap it up here, and you can answer these maybe offline for some of these other folks since we're running out a bit of time. But there was one question here. Let's see if we can get to. Do you have any modeling for nitrification of chlorine disinfectant? Any plans for research or anything in the works for this particular?
Good question. I don't have any experience on that particularly. I know one of the models we do have is a chloramine model that is able to look at monochloramine, dichloramine. Gosh, it's been a while since I've looked at this, but it handles a number of different species, and I believe ammonium is there. Gosh, I'm totally not prepared for this equate. So yeah, it doesn't go into nitrates in particular, but there is ammonia. But yeah, we don't currently have plans to do any further research. But if you look into a model, or if you have a favorite model and you would like to make it built in, we are happy to include further models. We actually hadn't included a new model in the last 10 years, 10 years, I want to say. But this one, we started talking with this researcher and added it, and we're able to easily add models. It's actually really easy to take a model and save it, and you can actually load or import a model from elsewhere. So it's a simple MSX file that you can pass between models to load them in. So yeah, that's a little bit on that.
Yeah.
Ben,
And it's definitely,
have you done that?
Yeah, it's definitely possible to do that. It's just more complicated. Like you can see here, there's how many different species, and this doesn't include some of those like nitrification type aspects. So I think there was a model you used a long time ago that was probably twice as many species as this, that was getting really into the weeds. So they can be very complex. It's definitely possible. So you just have to have to either have that research of what is the starting point and bring that in, like import it in, or start from scratch, because you can always start a blank model and type all those different things in. I think if you go to the terms field, like there's tons of equations in this one. Yeah. So it gets complicated.
This is the behemoth of a model. It's kind of the most comprehensive. So yeah, at least you could start from here and simplify things. I mean, of course, once you start to take away some of the reactants, it changes. Actually, one of the audience members mentioned that the built-in model is pretty academic and extensive, but there's a paper by George Castell, which I think is one of the co-authors In the paper, I was mentioning who has simplified this model a bit. So there's a vote from the audience that we add that model. So that's a good suggestion. Thank you. I also see a question to please explain again the F and S species. So if I come back to here, so yeah, so this is chlorine, this is THM. So what are F and S? So within water, there's organic compounds and different things that reacts with the chlorine, and it's not single things. It's a spectrum, and so we just kind of generalize what are the things that react with it quickly and then kind of go away, and what are the things that stay in the water and slowly react over time. So that's what F and S are. And in general, I didn't pick the right nodes to show it, but in general, we'll see that the F that comes out, it will as it comes out of the treatment plant, that F decays really quickly, and it brings down the chlorine. And usually it doesn't make it too far out. If I grab one of these nodes farther from the treatment plant, let's just take a look at the F out here. So it's 0.0024. Maybe it's still out here because the chlorine itself has decayed. Oh, no, it's not too low. It's kind of flatlining. But yeah, so the F usually decays. It creates that initial slope. That's how you use it. And then the S is what helps you calibrate that tail slope. So they each have a unique role in the equations. And it's really more of a spectrum of different reactants in the water quality.
And they also influence each other. So the chlorine is dependent on both the fast and slow decay, but then the slow decay, the slow reactant is also influenced by the chlorine. So they're kind of interacting with each other in multiple different ways and kind of feeding off of each other depending on how quickly they're decaying or not quickly.
Yeah, that's a good point.
Perfect. All right. Well, thanks everybody. Thanks for joining. Again, if there are any questions that were posted that we didn't quite get to, we'll be sure to follow up. Thanks, Nathan. Thanks, Ben. And we'll see you in 2 weeks.
All right. Thanks, everyone.
Thanks, everybody.